Hello, everybody, and welcome to the fourth meeting of the beer evaluation course. This time we will discuss brewing water and the mash. Just wanted to remind you that if you like the video, please hit the like button, and if you have any questions, please comment on the video and I will answer. If you haven't subscribed to my YouTube channel, please click the subscribe button and click the bell icon to get notified when my next videos come out. In addition, if you haven't followed me on my social media, you can see them changing on the screen right now or find them in the description below. And now, without further ado, let's get to our presentation of the day about water and mash. This is the fourth presentation of the beer evaluation course about the water and the mash. This is the layout of today's presentation. We will start by talking about the water cycle, then explain what is a mash, move on to talk about residual alkalinity, malt acidity and the mash pH, talk about common mash rests and their function, talk about different mash types, and finish with separating sweet wort from the grains via Lautering and Sparge. And let's start with the first topic of the day, the water cycle. The water cycle is a name for the path water takes on Earth. Water starts as gas or vapor in the atmosphere and form clouds. As the water form droplets, these absorb gases, dust, and mineral crystals that contaminate the water. When water falls to the earth as rain or snow and collect, they are called surface water. Surface water absorb organic materials and other substances. As water seeps to the ground, most organic matter is filtered out and more minerals are absorbed. Water gets out of the ground from wells or springs or from seeping into rivers and streams. Then they are evaporated back into the atmosphere and the cycle restarts. We distinguish between two main types of water. The first is groundwater. These water will have some minerals, but will have a lot of organic material in them. These organic materials will be mainly algae. The second type of water is underground water. These water will have a lot more minerals from the ground, but will not have organic materials because these are filtered out by the ground. The water that we get in our taps goes through a cleaning process that looks like this. The water are pumped from the reservoir to a water treatment plant. The first stage is to add coagulants that will help remove protein and other organic materials. Then, the coagulants are allowed to sediment and water are passed through a filter to remove the sediment. Next, sanitizers are added and allowed to work before transferring the water through biologically activated carbon to remove the sanitizers and also metals from the water. Next, specific compounds are added to the water like lime, chlorine, fluoride, and ammonia to help keep the water clean until they get to the faucet. Next, the water are transferred into a service reservoir and pumped from there to homes and plants. Now, we will move on to talk about a term that will be very important when we're discussing water that are used for brewing. This term is water alkalinity. Alkalinity is the amount of carbonate in the water. The amount of carbonate indicates three types of molecules: carbonic acid, bicarbonate, and carbonate. The main factor influencing how much carbonate is dissolved in the water is CO2 pressure on the water. The equilibrium between CO2 and carbonate determines the pH in pure water. Alkalinity is important to brewers because it works as a buffer for the pH, meaning the more alkalinity, the harder it will be for the brewer to change the pH of the brewing water. Another term we need to know about water is water hardness. We divide water hardness into two main types. The first is temporary hardness. These are carbonates that are at equilibrium with CO2 and can be removed easily by boiling the water. The second type is permanent hardness. Permanent hardness refers to the amounts of calcium and magnesium. These compounds cannot be removed easily from the water and will require special treatment to do that. After we talked about the water cycle and a few basic terms, it's time to move on to talk about the mash process. The mash is a term for hot water steeping process. The mash rehydrates the dry malt, gelatinizes the starches and makes them water soluble, releases the enzymes from the malt, and converts starches into fermentable sugars. During the mash, the crushed malt is mixed with water at 2 to 5 kilos per liter to achieve a temperature of 65 to 72 degrees Celsius. The equipment needed to perform a mash is first a mash tun. A mash tun is a large pot that can hold the water and the crushed malts. In some systems, called step mash systems, the mash tun will have a mixer and heating. In breweries that do a decoction mash, there will be another vessel to heat the grains in the process. We will talk about this later in the presentation. The mash tun can be the same tun as the lautering tun, and then it will have a false bottom. But in large breweries, these will be separated to save time. After defining what the mash is and the needed equipment to perform a mash, we can move on to talk about mash chemistry, mainly residual alkalinity, malt acidity, and the mash pH. Let's start with defining residual alkalinity. Malt contains phosphate that reacts with calcium and magnesium to neutralize water alkalinity. This reaction forms phosphoric acid that lowers the pH of the mash. A pale base malt only with distilled water mash will most likely result in a pH between 5.6 to 6.0. Residual alkalinity is defined as the alkalinity that remained after this reaction. A positive value means that the pH is higher than the 5.8 normal pH, and a negative value means that the pH is lower than that. But why do we need to care about the residual alkalinity of the mash? The reason is that enzymes are amino acid polymers that fold around themselves in a 3D structure. The 3D structure is dependent on the liquid pH, and if the pH changes, the structure changes with it, which might result in impaired ability to perform their task. Mash enzymes work best between 5.2 to 5.8 pH. Once the mash pH gets below 5, we will get a one-dimensional, grainy or roasty flavor, as well as impaired beta amylase activity. If the pH is higher than 6.0, we will get increased tannin and silicate extraction that will contribute astringency, harsh hop bitterness, and beta amylase impairment. But don't worry, as John Palmer says, beer and brewing is like food and cooking. This means that the same way a cook that wants to make pasta doesn't think about the pH of the water that they have at the tap. They just add salt. A brewer can use brewing salts to correct the pH of the brewing water and the mash to be within the required range. After defining residual alkalinity, it's time to discuss the main factors that determines it. Residual alkalinity depends on the grain bill and the water. Let's start by understanding how the grain bill affects the residual alkalinity. As we said, a standard mash with base malts like Pilsners, Pale Ales, Munich, or Vienna malts with distilled water will result in a pH of about 5.8. The pH decreases from the neutral 7 pH of distilled water as a result of reactions between calcium and phosphate. Other types of malts, like stewed and roasted malts, will have more acidity than pale-based malts. The most acidic malts are highly colored crystal malts. If we look at this table from a research paper by Kogi et al. From the Journal of the Institute of Brewing back in 2005, we see that they performed a standard mash for different types of malts. Malts that have no diastatic power had some degree of pale base malts added to them. Then, The researchers tested the levels of acetic acid in ppm for each type of malt. We can see how caramel and crystal malts affect the mash pH, reaching a peak at crystal 110. The second influencer about the mash pH or residual alkalinity are the ions composition in the mash water. The main ions that affect mash pH are calcium and magnesium. These are ions that react with the phosphate in the malt and creates acidity. Calcium is required at a minimum level of 50 ppm, but recommended values are between 100 and 150 ppm. Calcium is required for the activity of many enzymes. One of these enzymes is alpha amylase, which becomes more stable at high temperatures, and pH levels when calcium is present. Calcium also improves beer clarity by allowing the yeast to flocculate. Calcium does not have a flavor by itself, but the beer feels watery without calcium. The second ion is magnesium, which also reacts with phosphate. Magnesium is a vital yeast nutrient. Always remember that when adding calcium, magnesium should also be added. Other ions that are important are not related to the pH, but to the beer flavor. The first one to know is sulfate. Sulfate accentuates the hop's flavor and makes the beer seem more dry and crisp. It is especially important for pale ales and IPAs, and those styles often called for a minimum of 150 ppm of sulfates. If we are using sulfates along with noble hop varieties, it will bring out sulfuric compounds that are present in these hops. The second ion to know is chloride. Notice that it's chloride, not chlorine. This ion accentuates malt flavors and makes the beer taste fuller and sweeter. Another important ion is sodium. Sodium has the same effect as chloride, with enhancing the sweeter malt flavors. But as brewers, we want to keep sodium levels low, since in combination with other brewing ions like calcium, magnesium, bicarbonate, and sulfate, it can taste metallic. Two other ions are chlorine and chloramine. These compounds react with phenols to create chlorophenols, harsh-tasting compounds with a very strong medicinal smell like antiseptic. After getting to know the important players in water chemistry, we need to talk about how can we as brewers affect the alkalinity of the mash. We will start by reducing alkalinity. To reduce the alkalinity, we can use brewing salts, acid additions, and boiling. To reduce the residual alkalinity, the brewer can use brewing salts. These salts are mainly calcium sulfate and magnesium sulfate. To add sulfates along with the calcium and magnesium that will react with the phosphate in the malt. Or they can use calcium chloride and magnesium chloride to add chloride for malty beers along with calcium and magnesium. In addition, the brewer can add acid to lower the pH of the mash. These can be phosphoric acid, which is the same as what is in the malt, lactic acid, which can be added by acidulated malt, as well as concentrated acid, and citric acid. But make sure not to add too much lactic or citric acids, since their flavor will start showing up and you add yogurt or citric flavors into your beer. Boiling the brewing water is also a possibility. Since the amount of carbonate depends on the CO2 equilibrium, boiling will remove CO2 along with other gases, which will make the carbonate precipitate out of the solution and reduce the alkalinity. To add alkalinity, the brewer will usually use salt additions. These can be sodium bicarbonate, which is baking soda, or sodium hydroxide, which is caustic soda. But be very careful when adding the latter, since a very small amount can add a lot of alkalinity. Here you can see a table listing the levels of brewing ions in brewing water for many places in the world. Don't worry, you don't have to know this by heart. What I want you to take from this table is to understand why certain styles evolved in certain cities. For example, the levels of bicarbonate in London, Edinburgh, and Dortmund are very high, and that's why malty styles evolved there. On the other hand, the levels of sulfates in Burton-on-Trent are very high, and so pale hoppy beers evolved there. As usual in this course, the most important thing for us as beer judges is the flavor impact of the brewing water. To summarize, at a mash pH below 5.0, we will get a one-dimensional, grainy or toasty flavor and impairment in beta amylase activity. On the other hand, at a pH of above 6.0, we will get increased tannin and silicate extraction, harsh hop bitterness, and also impaired beta amylase activity. For ions, sulfate accentuates the hops, chloride and sodium accentuates the malt, calcium is needed for proper starch conversion and yeast flocculation, and sodium bicarbonate increases the alkalinity. After talking about water chemistry, now we can move on to talk about common mash rests, their main players, and their roles. We will go over these rests by order from lower temperatures to higher temperatures. The first rest is called doughing in. It is usually done in low temperatures between 35 to 45 degrees Celsius and lasts for about 5 minutes. This step allows for time to distribute the malt enzymes evenly through the malt and can result in a couple more gravity points. The next rest is beta-glucanase rest. This rest happens at 40 to 48 degrees Celsius for up to 20 minutes. Beta-glucans are gums that can make the lautering very difficult. But with today's well-modified malts, beta-glucans are broken down in the malting process, making this rest unnecessary. The next mash rest is ferulic acid rest. It can happen between 30 to 52 degrees Celsius and lasts for about 10 minutes. This rest activates enzymes that helps create ferulic acid. Ferulic acid is a precursor of 4-vinyl guaiacol, which is a phenol that gives the clove flavor in German Weissbiers. This rest is only done in German Weissbiers. Another rest the brewer can do is called protein rest. This rest is done between 35 to 67 degrees Celsius for about 15 to 30 minutes. This rest activates proteases and peptidases that breaks up proteins in the malt. The main purpose is to provide free amino nitrogen for the yeast to be able to synthesize new proteins. The second purpose is to create medium-sized peptides that help with head retention. But if this rest is too long, it can reduce the feeling of body of the beer. Notice that the last 3 rests share a temperature range and are usually done together. Now comes the 2 most important rests of the mash process. These rests are responsible for starch to sugar conversion, which is the main purpose of the mash process. The first of those is called beta amylase rest. This rest is done between 55 to 65 degrees Celsius, with 62 degrees Celsius where this enzyme is most active, and usually lasts 20 to 40 minutes. Beta amylase works by cleaving one maltose sugar unit from the ends of starches. The more starch ends, the more efficient it will work. This enzyme creates very fermentable sugars. The second rest is alpha amylase rest. This rest is done between 60 to 70 degrees Celsius, with 67 degrees Celsius where this enzyme is most active, and also lasts for 20 to 40 minutes. This enzyme cleaves starch bonds anywhere on the starch. This way, it creates large unfermentable sugar polymers. Again, notice that these 2 rests share a temperature range, and so they can work at the same time with alpha amylase creating starch ends for beta amylase to work on. In the same range, we have 2 more enzymes that are active. These are limit dextrinase and alpha glucosidase. Limit dextrinase is working between 60 to 67 degrees Celsius, and should work between 20 to 60 minutes. This enzyme breaks the smallest sugar polymers that alpha and beta amylase cannot work on, but limit dextrinase can convert them into fermentable sugars. Alpha glucosidase works between 60 to 70 degrees Celsius and should also work between 20 to 60 minutes. This enzyme can cleave glucose from both starches and small sugar polymers called dextrins. In every mash, the last mash rest will usually be mash out. This rest is done between 75 to 77 degrees Celsius for 10 to 15 minutes. This rest stops all enzyme action by denaturating them. It also makes the grain bed and wort more fluid to aid with lautering. It is essential for thicker mashes and mashes that contain more than 25% of the wheat, rye, or oats, but it's recommended for every mash. This table summarizes all the enzymes that are active in the mash, their active and preferred temperatures and pHs, as well as their function. You can use this as a quick reference. After talking about all the different rests and the impact of each one, it's time to talk about other factors that affect the mash and their flavor impact. The first one is the mash pH. As I said before, it can have a significant effect on both yield and fermentability. If the mash pH is below 5.0, beta amylase will be less active and work clarity can be a problem. At a pH of above 6.0, silicates and other tannins will be extracted from the husks and become a problem. The second factor is the degree of the crush. The finer the grind, the better the enzymes will be able to act on the starches and the faster the conversion will be. Even though the difference in yield is not great, the main advantage is the length of the conversion time will take. In addition to the pH and the degree of the crush, the brewer should also consider the water to grist ratio. At above than 4 liters per kilogram, it will dilute the enzyme concentration, resulting in slower conversion and lead to denaturation before they were able to complete the conversion. At below 2.5 liter per kilogram, the mash will be too thick and allow the enzymes to work fast, but it will create less fermentable sugars. The last factor to take into account is the mash length. Most of the enzymatic activity happens in the first 20 minutes and drops very steeply after 60 minutes. This is why the mash rarely lasts more than 60 minutes. Longer mashing times will create a higher degree of fermentability, so 60 minutes is recommended. This is where we finish the chemistry part of understanding the mash. Now let's move on to talk about the different methods a brewer can perform a mash. There are many methods to perform a mash, but in this course we will discuss the following methods: infusion mash, multi-rest mash or step mash, decoction mash, and the last one that is not really a mash, called serial mash. We will start with infusion mash. In this method, all the grist is mixed with all the water to achieve a target temperature between 65 to 67 degrees Celsius. In this method, only one temperature is used. The specific mash temperature flavor impact are at 65 degrees. We will get a very fermentable wort with highest yield, but we will have the least body since we favor beta amylase over alpha amylase activity. At the higher end, at 67 degrees Celsius, we will get a good yield, good fermentability, and medium to medium full body. This is the most common temperature. At the very high end, about 70 degrees Celsius, there will be a good yield, fuller body, and lower fermentability. This is suitable for low alcohol light ales or rich, fuller bodied beers. The second method to perform a mash is a multi-rest mash. Multi-rest mashing requires to add heat to the mash to increase the temperatures. This can be done by direct heating, meaning heating the mash tun while stirring to keep consistency, water infusions by adding hot water to achieve the next temperature, and decoction, which will be discussed next. This method gives more control to the brewer on the conversion process and sugar types that will be created during the mash. There are, of course, unlimited options in multi-rest mashes, but here are a few examples. For heavy beers, you can start with 20 minutes at 60 degrees Celsius, followed by 40 more minutes at 70 degrees to get a sweet dextrine malt. If you want improved gelatinization of starches and beta amylase activity, you can use 40 minutes at 63 degrees Celsius, followed by 20 minutes of 67 degrees Celsius. For under-modified malts, if they are used for more than 37% of the grain bill, you can use 3 steps at 50, 60, and 70 degrees Celsius. If you're making a German Weissbier, use 40 degrees Celsius for ferulic acid rest to create more clove phenols, followed by 2 saccharification rests of 63 and 70 degrees Celsius. The next mashing method is called decoction mash, and it is a version of multi-step mash. In this method, the brewer mixes the water to reach a target temperature. To get to the next temperature, the brewer removes a portion of the mash, heats it with a rest at around 70 degrees, and then boils it in a different vessel. Once the thick portion is boiled, it is returned to the main mash to raise the temperature for the next needed temperature. To reach the next temperature, the brewer calculates the amount of mash to boil to reach the next target. This method is better for under-modified malts, and it plays a key role in the development of malt flavors of Czech Pilsners and Munich beer styles. The next mash method is not really a mash. Unmalted grains need to be held in several temperatures to gelatinize the cell walls and makes the starches available for the enzymes. Usually, a cereal mash is done in a separate vessel and then added to the main mash. The procedure of a cereal mash goes like this. First, combine the grains with 25% by weight of base malts. Infuse the grist with 4 liters per kilograms of water. Bring the cereal mash to 45 degrees Celsius for unmalted barley, oats, rye, or wheat, and 63 degrees Celsius for corn and rice, and hold this temperature for 15 minutes. Next, heat the cereal mash while stirring to 68 to 70 degrees Celsius or 74 to 78 degrees for corn and rice, and hold for an additional 15 minutes. After this rest, bring the mash to a gentle boil for 10 to 15 minutes. Then, add the cereal mash to the main mash. This is not really a mash since we do not convert starches to sugars, but we free the starches. When the cereal mash is added to the main mash, the freed starches are broken down by the main mash. If you use pre-gelatinized grains like flakes or torrefied grains, you don't need to perform a cereal mash. Another type of mash that I want to talk about in this course is a partial mash. This mash is very common for homebrewers, so as beer judges, we need to know this process and its impacts on the mash. This is a method to add specialty base malts like smoked Vienna or Munich malts character to extract brewing. When we use 1 kilogram or more of malts in an extract brew, we need to treat it as a mash. To perform partial mash, place the milled grains in a bag. Keep the bag at 65 degrees Celsius for 1 hour. Increase the heat to 76 degrees Celsius and keep for 15 minutes. Remove the grains from the water and sparge with warm water to rinse the sugars. After this process, you can add the extract and continue regularly. Notice, to add enhancing malts like crystal or roast malt at lower rates, you can simply use steeping. No need for conversion. Now, after talking about mashing methods, let's move on to lautering or separating the wort from the grains. Lautering is the name of the process of separating the wort from the grains. The process is done as follows. The mash is moved into the lauter tun. Then, the brewer initiates the wort runoff to the kettle. In the beginning, the wort exits very turbid. To reduce this turbidity, the wort is pumped back to the lauter tun above the grain. This is called in German Vorlauf. When the wort is clear, the brewer starts collecting the wort in the kettle. When the water height reaches the height of the grain bed, the brewer starts to sprinkle warm water on the top of the grain to rinse the grains and remove as much sugars as possible. The possible flavor impacts of the lautering process are if the mash is moved to the lauter tun too fast and splashes, it can cause increased and fast appearance of papery oxidized flavors in the beer. There is also a risk of extraction of harsh tannins from the husks into the finished beer if the wort is drained too fast or if the sparge water temperature is above 79 degrees Celsius or with a pH of above 6.0. The equipment needed for lautering is a lauter tun. This is a big container with a false bottom. On the top, sprinklers are installed to rinse the grains during the sparge. In very wide or very deep lauter tuns, a slowly rotating rake will be installed to open the grain bed to allow drainage. And finally, after the lautering, we need to discuss the different options for the sparge process. Sparge means to sprinkle. This refers to the sprinkling of water above the grain. During this process, the brewer rinses the grains with hot water to extract as much sugars as possible. The sparge water temperature must be below 79 degrees Celsius and with a pH that's lower than 6.0, or else tannins and silicates will become soluble. There are several methods of rinsing the grains. In this course, we will discuss continuous sparge, batch sparge, party guile, no sparge, and the BAB method, which is also popular with homebrewers. Let's start with continuous sparge. This method usually results in the best yield. Sometimes it is called fly sparge. In this method, the wort is drained just until there are 2.5 centimeters or 1 inch of wort above the grain. The sparge water are then slowly added at the same rate the wort is drained. The process is stopped when the gravity is below 1.008 specific gravity or when enough volume has been collected. The next method is called party guile. This method was common in English brewing before the 19th century. This method allows the brewer to make 2 or 3 beers from the same mash, making different strength worts. The process starts with making a large mash and splitting the runnings. The first runnings were usually about 1.080 and were used to make aging beers. The second runnings were used to make a table beer. Then the mash was capped with more malts and water to produce a small beer. As we can see, this method gives the brewer more options to produce beers. Famous beers that are made this way are Fuller's ESB and London Pride as the smaller beer. The next method is batch sparge. This is another common home brewing practice. The process works by draining the mash completely. A second batch of water is added and mixed and left for about 15 minutes while the grain bed settles. Then recirculation is done again and the mash is drained again. This method is different from English party guile because the runnings are combined to make the same beer. This method is less efficient than continuous sparging by about 5%. There are some brewers who don't even perform sparge. It's much less efficient in terms of amount of malt, but it's easy and immune to tannin extraction since there is nothing that will affect the pH. To achieve enough wort, the brewer can create a large mash to produce enough drained wort at the needed gravity, or to create a high gravity wort and then dilute it to the target gravity. The last method we will talk about today is also common for homebrewers. This method basically turns tradition on its head by removing the grains from the wort instead of the wort from the grains. The process works by using the entire boil volume plus the retained grain water for the mash. The grist is contained in a mash bag that is steeped in the mash water. At the end of the mash, the bag is lifted from the tun and allowed to drain. At the end, the grains are discarded. Usually, the grain bag is not sparge, but there are systems that allow for sparge. This is where we finish the fourth presentation of the beer course about water and mashing. I hope that the talk was informative and interesting. I want to remind you that if you liked the video, please hit the subscribe button, like button, and click the bell icon to get notified when the next videos come out. If you have questions, please write them down in the comments. I promise to go over them and answer. In addition, you can see my social media handles change on the screen or find them in the description of this video, and you're welcome to follow me to know when my next projects come out. Thank you for listening. I was Omer Basha, and see you in the next meeting where we will discuss hops and the boil.